This is video 29 in the series of reinforced concrete slabs. In this video, we will give you an example of how to calculate foundation blocks with the method of strut and tie. We have a foundation block with a total load of 1050 kilonewton in ultimate limit state persistent. There are two piles, it's a symmetric block, and there are some dimensions given as is stated in this figure. First of all, we will check if this is a D region or a B region. For the D region, the span must be smaller than 3 times the height of the block. So 4 meters is smaller than 3 times 2500. So we are in a D region and we cannot use our concrete tables and we have to use the strut and tie model. The effective depth of the foundation block is then equal to the total height of the block, which is 2500, minus the position of the inclined strut. The strut starts at a depth of y0. We will take it standard as 100 millimeters. And at the bottom, the tie is the centroid of the tie is at a position of 2 times the concrete cover from the bottom of the slab, from the bottom of the foundation block. So this gives us an effective depth of 2300 millimeters. The angle of the strut is then the tangent theta, the tangent of the strut is then equal to this equation. And we have 1.19 of the tangents, and this is between the limits, like between the limit 1 and 2, so this is fine. The angle is then 50 degrees. It's smaller than 55, so we do not have to increase the permissible stresses. Forces, the normal force in the column is then, of course, NED is 1050 kilonewton. Direction force in the piles, because of symmetry, is half of it, 525 kilonewton. The normal force in the strut is then the reaction force in the pile divided by the sinus of the strut angle, and it gives us 684 kilonewton. And the tension force in the tie is then the reaction force in the pile divided by the tangents of theta, gives us 439 kilonewton. The note at the column, the maximum allowable stress, then the K factor is 1. Then we have 15 megapascal is the maximum allowable stress. And the compressive stress at the node on top at the side of the column is then the force divided by the surface, and it's 11.67 megapascal. And at the side of the strut, it is 11.66 megapascal. So you see that even if when you calculate it separately, you will see that this node, which is in compression at all sides, it's an hydrostatic stress situation. When we can make now a small sketch, then you see this is the node on top of the foundation block with the acting force 1050, gives you a stress of 11.65, and then on the left and right hand side we have a similar stress application coming from the concrete struts. The maximum allowable was 15, so this is all right. The pile node 1, the maximum allowable stress is calculated with K1 equals to 0.85, so it means 12.75 megapascal. The actual stress is the reaction force of the pile divided by the surface just near the pile, and so we have 8.4 megapascal, which is smaller than the 12.75, so this is fine. The same at the size at the side of the strut, it's 8.4 megapascal, and the pile on node 2, it's exactly the same situation. So now the 3 nodes are checked, the one on top and the 2 on the bottom of the foundation block, and those nodes are okay regarding the maximum allowable compressive stresses. A small sketch shows that when for the left hand side node, you have direction force of the pile 525, which gives you a stress of 8.4, and the stress on the plane or on the surface adjacent to the concrete strut is also 8.4 megapascal, and the tie is 439 kilonewton. The stress in the strut, the maximum allowable stress is the stress with K1 equals to 0.6. It gives you 9 megapascal. The length of the strut is then the effective depth of the block divided by the sinus of theta and gives you 3 meters. And the cross section of the strut, well, this is a little bit more complicated. Remember, we have a strut fanning out and then fanning in again. So we have to calculate the DSO1x and the DS11x, and then the same in the y direction. DSO1x, we've seen that we can use this formula, and we can work it out gradually, and you will see that we end up with 1504 millimeters. So the DSO1x, this is this diameter, is 1504 millimeters. The diameter in the other direction, DSO1y, again, we will use the formula like we have seen in the previous slides. And when we work this out, we have 700 millimeters. You see here clearly that the limitation to B, to the width of the block, is now dominant here for the Y. It means that the strut cannot fan out in the direction of the width of the block. So the width of the block is limiting the fanning out of the strut. So now we have 700 instead of 1504. We do the same for the lower part of the bottom part of the strut. When the pile section is much different from the section on top of the concrete block, then you can have a large difference between DSO1x and DS11x. Therefore, we will recalculate for the bottom, and we have 1504 millimeters. And in the other direction, we will have the same. It is limited by the fanning out of the concrete strut, and it's 700 millimeters. Now we will look at this surface on top of the strut. It's the surface of an ellipse, and it's P/4 times the 2 diameters. It's 827,000 square millimeters. The surface SO1 on top is 59,000 square millimeters, and then on bottom we do the same. S11 is then 827,000. It's almost the same as the top, and on the bottom it's 81,000 square millimeters. Now we have all the different surfaces. So the stress in the strut now is the normal force, normal load in the strut divided by the mean surface of the top surface, and then just the surface just below it, which is SO1 and SO1. This is SO1, this is SO1. And we have 1.54 megapascal. And the compressive stress in the surface just below that, it's 1.51 megapascal, and this is much smaller than the 9 megapascal which is allowed. So the stress, the strut complies with the maximum allowable concrete stresses. But because of the fanning out of the the strut. We create some internal tension forces in the strut, and then we have to calculate them. We use the formulas that we have developed in the previous slides. We put in some numbers, and we see that this tension force is 155 kilonewton, and in the other and the lower part is 145 kilonewton. This stress, then that's for the other direction. And this tension, we have to take it up with reinforcement or with the tensile stress, allowable tensile stress of the concrete. So the mean allowable tensile stress is 2.56 megapascal, and the tensile stress in the strut, is then the tensile force divided over an area which is 0.25 over 1/4 of the total length of the strut, gives you 0.3 megapascal, and in the other side it's 0.28, and at the lower side is 0.09 and 0.10. You see immediately that the tensile stresses created by the fanning out and the fanning in of the struts are very small. They are less than 1/10 of the allowable stresses. So in most cases, you will not need to put additional reinforcement to cover this. The reinforcement tie is just the total tensile load divided by the yield strength. It gives you 1009 square millimeters. This amount of reinforcement, we have to define a strip, and the depth of the strip is 100 millimeters, and the width of the strip is of course the width of the foundation block, which is 700 millimeters. So the amount of diameters and the diameter, we see that we can use 2 diameters of 32 will be fine, but 2 diameters of 32 is 1600 square millimeters, but we only need 1009. So there's a little bit of a waste. So we can use another diameter, for instance, diameter 25. We calculate the total amount of rebars needed. So it's something more than 2. So 982 is too little for the amount we need. We try again with a diameter 20, and then we got 4 diameters 20, which is also a little bit waste of rebar section. And then we can use diameter 16, and then we have 1005 square millimeters. So now you can 1005 or 1009, it's almost the same. You can use 5 rebars diameter 16, or you can make a combination, of course, of rebars. And here we have chosen for 2 diameters 20 plus 1 diameters 25, and then you have enough reinforcement. Minimum reinforcement. This is our foundation block, and the minimum reinforcement says that the distance between or the center to center distance of the reinforcement bars must be smaller than 30 centimeters. Minimum must be larger than 150 square millimeters, and it is 1.1% of the surface of the concrete in all directions. So now if we look at surface 3, for instance, and surface 1 and surface 2, then we have the 3 surfaces, and we'll look for how much in general, how much reinforcement do we need as a minimum reinforcement. So we see that it will be in total, we will need something like 0.0244 cubic meters of steel, of rebars. And you can transform it into 24 kilograms of reinforcement per cube of concrete. So we have to define 3 cages of stirrups, closed stirrups, that are fulfilling the role of minimum reinforcement. To do so, we can make a rough estimate by using this little formula, which gives you the diameter of the minimum reinforcement in function of the spacing between the reinforcement and the two sides of the surface that we are considering. So when you consider the surface, for instance, 2500 times 700, which means this is surface, this is surface 1, 700 times 2500, this is surface 1, this is surface 2, and this is surface 3. And you apply this formula for different spacings, as is what if you take S equals 300, which is the most economical one, then you see we need something more than a diameter 10, but on the larger surface we need something like a diameter 18. So that's a little bit, that's a lot for minimum reinforcement. So we take a smaller spacing. S is 250, then we have 9.2, that's fine, 9.8, that's also fine, and 15.9, okay, that will be fine. We just have a look at a smaller center to center distance, and then we have 8.3, 8.7, and 14.3. The 14.3, you have to round it off for a diameter 16, the 8 for a diameter 10, and this 8 also for diameter 10. So it is obvious that this solution is the best choice. So we will have 3 cages of stirrups where the distance between the center to center distance is 250 millimeters and the diameters is 10, 10, and 16. The diameter 16 is for a stirrup doing like that, this, and from there to there. There's a diameter 16 every 250, and in the other directions, it's a diameter 10 every 250 millimeters. This is now a very long calculation for a very simple basic problem. So what do we observe? We observe that the concrete compressive stresses are independent of the strut angle. We see that the concrete compressive stress in the struts are rare not to comply. So it means they comply all the time. And this, of course, is that the stresses at the nodes, they must be okay. So that you have to check always. But when the node stresses are okay, then the compressive stresses inside the struts, they are most of the time also always okay. So in practice, at normal geometrical dimensions, just normal geometrical dimensions, there is no need for an internal reinforcement. And because of that, we will introduce a simplified method for common cases. And the simplified method for the checkup of stresses in the struts is easy. At a column side, there is a surface which is A0, B0 divided by 2 sinus theta. At the pile side, this is the surface at the pile side. And what we will do is the surface where we will check the compressive stress in the strut is the minimum of those 2 values. And those 2 values, it is just proportional to the maximum permissible stress node and strut. That's where this is coming from. This 1 divided by 0.06 is at the node column, and at the node pile it's 0.85 divided by 0.6, and this is 17/12. So it is just the minimum of the 2 values here, and that's the only that's the easy way to calculate the surface of the struts where you have to check the maximum allowable stress, and it's much easier and much faster to do. And then just the stress in the strut is then the force, the normal force in the strut divided by this calculated surface. Of course, you always have to check if the cross section that you use here as S, if this cross section can develop perpendicular to the axis of the strut. This is a check that you have to do. Otherwise, it can happen that this surface is going to be outside the foundation block, and this is not right. So you have to limit this to stay inside the block. So you have to check this cross section S. And we assume that the struts have enough space to spread